Welcome back, everyone. In this lecture video, what we're going to do is we're going to look at that same problem. However, we're going to see how we can approach it through classification. Remember, we had that fair class column, 0 or 1. So we're going to show you how you could approach that same problem if it was a classification. And because pretty much 95 to 99% of all the code is pretty much the exact same, instead of typing it all out again, instead we're going to open up the lecture notebook and show you and highlight the key differences of what you would have to do to actually work with it as a classification. Let's go ahead and get started. Okay, here we are at the notebook for the classification. And I want to note here, so this notebook is previous from the regression notebook, and so it's called 4B, full ANN code along classification. And it's extremely similar to the regression notebook, which is why we're actually not going to code anything, but instead highlight the differences of how you would approach this same data set if you were to use the fair class column. So the fair class column basically predicts whether or not a fare is greater than or less than $10. So we do the same imports we did last time. We load up the data set in the same way, but what we're going to do is we're going to focus on this fair class column here, which is either 0 or 1. So we're dealing with a binary classification problem. 0 if it is not greater than $10, 1 if it is greater than $10. So you can see here this $10.10 ride has a fare class of 1. These other two first values that are less than $10 have a class of 0. And so we check out the fair class. It's always a good idea to do value counts, which is essentially a group by with a count. So it counts per different or unique class. So there's 80,000 instances of 0 and 40,000 instances of class 1. So conveniently, around 2/3 of the data have fare under $10 and 1/3 have fares $10 and above. Okay, so we have this sort of classification. Then what we still do is the same feature engineering we did before. None of that feature engineering changes just because it's a classification problem. We still calculate that distance. We still do the date, time, column, and derive useful statistics from this. So we still do all that. We still separate the categorical from continuous. So same code we use there. We still use the pandas category data type. So we do all that. And nothing's changed since last time here. Go ahead and grab those values and then convert those NumPy array to tensors. So we're still doing all that. We still set the embedding size the same way. And if you'll notice, our tabular model is going to be extremely similar. So let me go ahead and show you where we actually differ. So right here is the breakdown of the embedding steps that we did last time in the other lecture series. Still scrolling down. And you'll notice that the main thing that's going to change here, if we keep scrolling down, is the actual output layer. You'll notice that we still have this output size parameter as a call, but when we actually create the model, we set the output size as 2. And what we're going to do is we're going to set output size to however many classes you have. In our case, we had a binary classification problem, so we set it to 2 since we have either 0 or 1. If you had 3 classes, you would set it to 3, 4 classes 4, and so on, because you want in the output layer 1 neuron per class, as we previously discussed in the theory lectures. And then what we're going to do here is in our loss function optimizer for our criterion, we'll go ahead and use cross entropy loss. Previously, we used MSE. So for classification, we'll replace that mean squared error loss function with the cross entropy loss. Okay, so you can see already those kind of two main differences there. We still perform the train test splits as we did last time. We have our training data and test data. We go ahead and train the model. Just like last time, I should mention our data set has already been shuffled. So that's already randomly shuffled as noted there. We go ahead and train the model. Here we train it for 300 epochs. And then we can plot the loss function. You can see that it trains quite a bit faster than it did for regression because this is kind of a simpler problem to kind of predict whether something is less than $10 or greater than $10 is a little easier than trying to predict the exact dollar value. So we reach a lower cross entropy loss at almost half the epochs that we did than last time for the regression model. We validate the model in pretty much the exact same way. We're still calling that same criterion. And then what we can do is we can go ahead and look at the first 50 predicted values. So here we can do argmax to get those values, just as we did in previous classification theory problems. So we did here, we can see here that the greater the value in this output tensor is essentially that's what the neuron thinks that the class it belongs to based off its index position. So 1.8 is greater than negative 1.6, so argmax happens at 0, which means it goes ahead and predicts that the class output should be 0. So you can see here we did incorrectly, correctly, 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 and so on. So here's another one that was incorrect, and you can keep going down. So here we can just compare the ones we got correct versus the ones we got incorrect. And we got 45 out of 50, so about 90% correct. So we have 90% accuracy. And if you come back here, you can actually see how we're calculating accuracy. We're essentially keeping track of how many we got correct by checking where the argmax of the item happens to be equal to that y test value. And then we divide that by the actual number of rows we're testing. So 100 times correct divided by rows, that's essentially our accuracy metric. Okay, so we're getting 90% accuracy. You save the model in the exact same way. Here we show you how to load that saved model from scratch. Main thing to note here is we have an output size of 2, load it the exact same way, and then our test input is essentially the same as we did before. And here we have the predicted fair class is 1. Okay, so you can see that it's extremely similar. I'm going to highlight real quick what the main differences were. The main difference here was the output size. You're going to edit that based on however number of classes you have. And the other main difference is your criterion for measuring loss. It doesn't make sense to measure classes with mean squared error. So instead, when we're actually defining that, we'll use cross entropy loss. All right, and that's essentially it for converting a ANN from regression to classification. Of course, that assumes that you already have that label column. So now you should be able to deal with your own data sets and use either this notebook or the previous notebook as good blueprints for you to follow, depending on if you're performing a regression problem or a classification problem. Thanks, and we'll see you at the next lecture.